let's hope it stays. So, thanks for organizing this. And what I'm briefly going to talk about today is an exercise we're doing in detecting bird sound in unknown acoustic background using crowdsourced data. I'll explain in a minute what that means and what the rationale is behind that. I'll show some results, basically on GMM density estimation, basic techniques that we use them that are in the paper, and then some more recent work we're doing with HMMs on that. And I'll conclude with what we do now and what we hope to do in the near future. So, the basic idea that most of the presentations today start from is that we now have lots of recordings from all kinds of different. The two main modalities of doing that is having unattended recording stations, as Gianni explained at the beginning. And another way of doing it is having the general public using their mobile phones and collecting recordings, which is another promising way of doing it. The issue there is that such recordings are usually very sparse, or sparse in bird sound. They have all kinds of other sound or no sound sources at all. And when we, as is most of the work that is done nowadays, as is the classification, ongoing classification, competition, other competitions are, the goal being to classify between different species. The objective there is to classify a recording, a part of a recording that you know that has bird in it. But in realistic situations, most of your recording doesn't have anything, or has other kinds of sound. So the question is, which is very difficult to model. I mean, the background is so diverse, it's very difficult to model specifically. So the question is, can you build normality models of each species of bird and then use anomaly detection type of techniques where you estimate, you build a density model and you estimate how well that fits a given bird model and say that you have detected it when you hit a certain threshold. So these kind of results I'm going to go through in a minute. The main point here is that we try to do what we're doing in a scalable way. So whatever we do, we try to do it in a way that can scale to very large collections without manual pre-processing or annotation, for example, other than the one that is provided already by crowdsourcing, as in Sinocanto, for example. In the last presentation, we saw how you can, and that's very typical in bird song analysis, you can do some sort of linguistic, kind of subjective to some extent modeling, where you say this is a syllable and this is a phrase or so on. But first of all, this is subjective, but more importantly, this is non-scalable. You can do it for a few seconds or a few hours, but then you cannot do it for all the diversity of bird sound. So this type of work where you try to build a model that is based on syllable segmentation is very nice, but I don't think it is scalable. We can hope, I don't think we can hope to do that for the around 10,000 different species of birds that are around, ever. So can we use a very simple techniques that I'm showing to try and sidestep that by using whatever annotation we have in Sinocanto, so in crowdsourced databases, and our example is Sinocanto that we're using here. I should say that the objective here is not to classify between different species. The objective is to try and see if you can locate where bird sound is in a sound excerpt that has all kinds of other different sound sources. So most of you know this stuff, given the ongoing competition and so on. Sinocanto is a very good, is a sustainable source of training data. Over the last few years, it has grown to cover most of the existing bird species with at least one recording, and in most cases with many more recordings, and it keeps growing. Sorry, going the wrong way. And you know, it has a very healthy sort of intake of recording, so we can hope for this thing to keep going and provides a sustainable way of training data. Now, recordings in Xenocanto have very limited annotation. Well, they have annotation in terms of what species are there, but these are by users. Sometimes they're right, sometimes they're wrong. But if you use the API that they provide to limit yourself to recordings that are labeled as quality A, so the sort of best kind of quality, and you twist the API a little bit to just take recordings that don't have any other birds in them, you end up with recordings like this. For example, this is sorry about that. Anyway, this is robin. It has song in it, and then silence, and then song in it, and in some cases you have lots of silence and a little bit of song, and the other way around. When we want to build a normality model of that specific species, we'd like to have just bird sound in it, using the simplest way, which is to use a Gaussian mixture model to model a density estimator of the features that you extract. You can ignore time sequencing, and just by using 10% of the monoenergetic frames, you end up with something like that. If I ever get it to point to the right one. So this is just frames concatenated. You make sure that there's no silence. Well, the point here is, oops, sorry about that, yeah. The point here is that using the annotation that's already there, so good quality, which means that whatever is not bird is very silent, and using just recordings with R annotated, just having that bird, you can obtain data that's very rich in the sound of that bird. And for the results I'm showing here, we just use plain spectrogram, so no worries about misrepresenting harmonics and so on, which are very valid, by the way. Just take spectral features, just normalize each frame to a PMF, and we try different features and see if we can fit a Gaussian mixture model density estimate to these, and then use the likelihood out of that to and see how many times we get it right in telling what is bird against what is not bird in different backgrounds. We use very standard sort of expectation maximization models for fitting the GMM. And we use minimum description length to estimate the proper number of components in the GMM. So this is very bog standard, but there's, you know, the point here, what can we do to make it better? So I'll show the results of that, which is the main part of today's. Oh yeah, so what we test on. Of course, another point is that Xenocanto is very diverse. You have recordings from different places, different recorders and so on. But again, for example, in a very recent paper by Dan Stowell, when you use that for training and different data sets for testing, you get a quite significant reduction in performance compared to when you train and test on Xenocanto recordings. So I'm not going to say much about that because I'm not sure as to what the significance of that is, but sometimes it seems important to separate. And also for the purposes of what we want to do here, which is to find exactly the limits of the bird sound. I'm going to explain that in a minute. We want to have clean recordings of bird. So we're using another database, which is a Berlin Museum for the Animal Sound Archive, anyway, that's what it's called, the Tierstimmen Archive, that gives very clean recordings of bird for a number of species. Around 200, and quite a few recordings. So you get just bird. You have very short or longer recordings. In some cases you have recordings that have silence in them. Yes, so there was silence in there. But generally, this is very good. This is the kind of cleanest and best annotated type of recordings. And then we embed these in We use 15 species, the ones that there's more than 100 recordings in the TR-Steven archive for each one of them. Details of that are in the paper, so anyone who wants to know the details can run through that. And we then embed that into noise. We use noise from existing databases from previous competitions of different urban setups, and we end up with a test example like that. I don't know how we do that. So we heard, and then we used the likelihood of the Gaussian mixture model to as an indicator of the likelihood of that being bird or not against. So this is a very simple sort of anomaly detection situation where your normal is the bird and everything else is anomalous, and you want to detect against that. So for example, in this case, it did very well. It says that the very low likelihood of bird here, and it detects the bird quite well. So when we run that, as I said, we have different selections of features, standard features, which are just spectral features of the frame, so the highest frequency, the point of the highest frequency, and then you can use the standard deviation and the mean, and spectral flatness measure, and so on. When we do that over 50 tests, as the one I showed, and just to explain it a little bit better, just for a minute, what this. So then we compute standard receiver operating characteristics curves, which is, we have ground truth. This is not bird, and this is bird, bird, not bird, and so on. So you compute the curve of true positive rate against full positive rate for different threshold selections, and the best classifier would have an area under that curve being equal to 1. A classifier that classifies by chance would have, so the worst classifier would have a curve that has an area under it, which is 0.5. So just to put it very briefly, numbers here that are close to 1 are excellent, and numbers that are close to 0.5 means chance, that the classifier doesn't know what it's doing at all. To put it very, very briefly. And just by using the one feature, which is the position of the highest frequency, which is the most informative feature anyway, these are species, so these are the 15 species that I went through. You get very good results in most cases, but you get very bad results in some cases. These are nightingales, the common nightingale, and this is I think the thrush nightingale. Yeah. So the hope here is that, as is the standard in anomaly detection problems, to try and build a richer model of, put more information into your normality model and separate better against background. And that doesn't really work that well when we try to do it by including more features. There's more examples in the paper. You actually get the same or worse results. So this doesn't look like the way to go, just by stupidly adding more features of standard spectrogram statistics. Doesn't do anything. So what we're doing now is, all this doesn't encode at all time sequencing. So this is just frames, the distribution of spectral features over frames. It doesn't say what frames come before and after. Standard way of doing that would be to try and feed an HMM to that. Now, there have been previously some attempts to do that, and most of them, if not all, these few attempts were based on fitting HMMs to syllables. So they were restricted to very few species, because you can only get enough training data, syllable data. This is very expensive manual work to do that. So the idea here is, can we use the annotation of Xenocanto to not get syllables, which we cannot, but in an automatic way get sort of parts that are sequences of clean bird in them. And if you run a very simple thresholding algorithm, just get segments that have more than 50% in them, frames that are more than 50%, have more than 50% of power of the more powerful frames. As I said, in Xenocanto quality A recordings, most of the non-bird is nothing. is silence. So you can rely it can be a good thing to rely on to say that whatever is not energetic, I don't care about, and what is energetic is bird. If you just use quality A solo recordings from Sinocanto. And you get recordings like that, for example, or other phrases like that. Or if you take a little longer, 500 milliseconds, for example, for nightingales, there's a little bit of human speech in there. So that's not very bad when you're doing normality models, anomaly detection. Your main assumption is that most of the data, nearly all of the data, is from the normal class, so from that specific bird species. So I don't have full results on HMM modeling yet. I just did that over a few days. But standard, again, maximum likelihood fitting, Baum-Welch fitting, gives log likelihood like that. So, for example, if you try on this test,
Just now, 5 steps there for 5 weeks. Your lovely brassicas for 5 pounds. All those brassicas there for 5 pounds. Move on to that one there, 5 weeks.
oh, it doesn't show the timing thing. It should. Anyway, trust me, it's in the right time. I mean, these are the limits of the bird, and this is the log likelihood of the fitted HMM. And you know, this is just an example. It's not, you know, full test results with any statistical significance attached to it, so I'm not making any claim that it's going to work well or bad or better than the GMM fitting, but sort of, it seems to be working. To not spend much more time, I'll, how much do I have?
5 minutes.
Okay, so yeah, we can listen to that one. Generally, as I showed before, the Nightingale ones, the Nightingale models don't work as well. This is probably because of the fact that Nightingale's frequency shifts much, and we have verified that by seeing the GMM, the Gaussian mixture fitted models. They shift closer to sort of urban noise, so just using that one feature expectedly doesn't work. In this case, it does pretty well, especially when you use the spectral flatness measure feature as well, which is the red curve. As soon as the bird comes in, so the log likelihood model increases. So, stop that. Yeah. So that's mainly what I had to present. Just to spend another couple of minutes to what we're doing now. So first of all, I think quite important and very simple thing is that it seems that you don't need to really worry about syllables to start with. There's lots of literature, especially the earliest literature was about fitting sort of linguistic type models to birdsong, because birdsong sounds a little bit like human language, having phonemes and syllables and so on. That might be very right and interesting, but it doesn't really help, because in human language we have very detailed grammar models, syntax models. We have a very easy way of obtaining phonemes, syllables, because we can tell humans to tell them, and we can obtain large data sets. With birds we cannot. So it doesn't really, worrying about doing proper linguistic modeling of birdsong, I don't think it has lots of mileage in terms of being scalable. But using crowdsourcing data like Sinocanto, you can very easily obtain clean phrases which you can train on. And what we showed here is that using the simplest, the most bog standard way of building a normality model does work. Not as well as one would hope, but it does work. The main direction which one would take to use more features doesn't really show much promise, but using HMMs, using time sequencing, rather than simple density estimation models, might work better, and that's what we're working on now. Doing it in a very simple way doesn't work with HMMs, because there's lots of parameters that you have to tune, and there's no way trying to heuristically tune them. So we're working with sort of Bayesian treatment of the modeling, and which I have no results for to show today. Generally, using simple spectral statistics features might not be the best idea, so we might have to be a bit more clever on that. And finally, we need, well, the most important thing is that I didn't show any actual threshold. To actually apply that, you need, and the most important problem in normality detection is to set an actual threshold. What I showed now is how well the classifier separates between bird and no bird. So it makes sure that bird will always have, or most likely have, a higher likelihood than non-bird. But finding a number after which you say this is bird or this is not bird, that's another problem, and that's what we're working on. There's structured ways of doing that for GMM models, extreme value theory methods and so on. And for HMMs, it's a little bit more cross-validating type work, but we're working on it. And hopefully soon we'll have tests on real field recordings of that. So so that's what I have to present. Thanks.
Just one question. Sure. You don't consider the time patterning of the sounds, but the time patterning is often a key for recognizing that is a bird singing.
With HMMs, you do. That's. I didn't do that. We didn't do that for the Gaussian mixture model, where you just take frames and you.
Yes, but the main goal of your work is to be able just to separate birds from others, or also to recognize correctly individual species.
The main goal is the main goal in this one is to detect. Now this is a very interesting question, and thank you.
So to separate the garbage from birds.
Yes, and then you can feed that into an extra level of classification. What I wanted to say is that a classifier that has 1,000 classes, as you mentioned, is a notorious. Even if they're separable, well, they're never perfectly separable to start with. Yeah. You never know how it will generalize. Even if your training examples are separable, you don't know what the real world is. But the statistics of 1,000 classes is very complicated anyway after a point. And getting balanced testing situations and balanced training situations for 1,000 classes is very difficult.
Excusez-moi, juste pour vous donner un repère de temps, dans 5 minutes, vous pouvez commencer à descendre pour le buffet.
D'accord, merci. Was that in 5 minutes we have to go down and eat?
They just recall us to take some food sometime.
Okay,
in 5 minutes.
I'll just answer that if that's right.
No, that's fine.
And the point I was making is that in real situations, there's not a place in the world where there's a realistic, likelihood of 1,000 birds being there at the same time of year. I mean, so humans don't do it this way. No human expert could have in their head the calls of 1,000 birds or 10,000 birds. So if you know what is bird, so coming back to your question, if you know what is bird, and you can look for the birds that are likely to be there at that time of year, then you can classify, and you can have, for example, a lazy classifier where you can plug in classes, like a nearest neighbor type classifier, depending on where you are in the world and what time of the year it is, taking that information into account beforehand, before going into the classification stage. So, thanks for the question. Yeah?
Just a very short comment. You said that your features, they are not that good, like you didn't find that putting more features is going to improve your result, but maybe it looks to me that actually they are very correlated features. That's why you're not taking any improvement out of
That's true, but if you're using a full covariance matrix in the GMM, that takes care of that. So that should be all right. Yes, of course, if you were expecting the features to be independent, and if you're using diagonal covariance matrices, then that would be a problem. But in this case, we take that into account. So that shouldn't be the problem in these results. Generally, this is an issue, and generally, yes, some of them are correlated, especially the mean and the mode. Obviously, they are not independent anyway.
Did you play with PCAs and LDAs to try?
Yeah, you can do that. I mean, the main, yes, you can do that. The main, one of the points here, and one of the reasons we use simple GMM fitting is you have some interpretability. Like you can see, for example, if the models are consistent in different runs of the training process for different selections, because you have so many, within a country, you have so much training data, you can take parts of it and see if the models are consistent, which they are in most cases. When then you do PCA and so on, you lose a little bit of that interpretability, so that's why I didn't go into that here. And in any case, yeah, just the one feature, in which case you don't have any of these issues, worked very well, so it doesn't really...
If that's the case, that's the case.
Yeah.
So just one question. You compare result with non-discriminative version of your approach, purely discriminative one. For example, you plug an ESVM and
Well, the thing is that if it's non-generative, so it's a discriminative method, it's not, well, anyway, as a point for discussion, really, this has to be generative, because you don't model the other class at all. If we have the chance to model the other class being the background, if you know what the background is, then this is a trivial problem to solve, clearly. I mean, if you know that it's traffic noise, you take lots of traffic noise, you model that, and that's very easy. Any classifier would work fine. But an SVM, without knowing what the other class is, then you cannot discriminate against it.
Or any one class, for example, in terms of anomaly detection, or stochastic methods. So applying one class is